Hello, I'm Neha. In this video, I'm going to talk about API gateways in microservices architecture. In a microservices architecture, each microservice exposes a set of fine-grained endpoints. This fact can impact the client to microservice communication. We need to decide how the client accesses these services. Let's look at the options. Direct client to microservice communication. A possible approach is to use a direct client to microservice communication architecture. In this approach, a client can make requests directly to some of the microservices as shown in the diagram. A direct client to microservice communication architecture could be good enough for a small microservices based application, especially if the client app is server-side web application. However, when you build a large and complex microservice-based application, and especially when the client apps are remote mobile apps, that approach faces few issues. Consider the following questions when developing a large application based on microservices. How can client apps minimize the number of requests to the backend and reduce chatty communication to multiple microservices? Interacting with multiple microservices to build a single UI screen increases the number of round trips across the internet. This increases latency and complexity on the UI side. Ideally, our responses should be efficiently aggregated in the server side. This reduces latency since multiple pieces of data come in parallel and some UI can show data as soon as it is ready. How can you handle cross-cutting concerns such as authorization, data transformations, and dynamic request dispatching? Implementing security and cross-cutting concerns like security and authorization on every microservice can require significant development effort. A possible approach is to have those services within the Docker host or internal cluster to restrict direct access to them from the outside, and to implement those cross-cutting concerns in a centralized place like an API gateway. How can client apps communicate with services that use non-internet friendly protocols? Protocols used on server side like AMQP or binary protocols are usually not supported in client apps. Therefore, requests must be performed through protocols like HTTP, HTTPS, and translated to other protocols afterwards. A man in the middle approach can help in this situation. How can you shape a facade especially made for mobile apps? The API of multiple microservices might not be well designed for the needs of different client applications. For instance, the need of a mobile app might be different than the need of a web app. For mobile apps, you might need to optimize even further so that data responses can be more efficient. You might do this by aggregating data from multiple microservices and returning a single set of data, and sometimes eliminating any data in the response that is not needed by the mobile app. And of course, you might compress that data. Again, a facade or API in between the mobile app and microservices can be convenient use for this scenario. Usually, a much better approach is to use what is known as API gateway. An API gateway is a server that is the single entry point into the system. It is similar to the facade pattern from object-oriented design. The client gateway encapsulates the internal system architecture and provides an API that is tailored to each client. It might have other responsibilities such as authentication, monitoring, load balancing, caching, request shaping and management, and static response handling. The diagram shows how an API typically fits into the architecture. As you can see, it is a single entry point into the system. The API gateway is responsible for request routing composition and protocol translation. All requests from client first go through the API gateway. It then routes requests to the appropriate microservice. The API gateway will often handle a request by invoking multiple microservices and aggregating the results. It can translate between web protocols such as HTTP and WebSocket and web unfriendly protocols that are used internally. An API can provide each client with a custom API as well. Let's look at the main features in the API gateway pattern. Depending on the product, it might offer richer or simpler features. However, the most important and foundational feature for any API gateway are following design patterns. Reverse proxy or gateway routing. The API gateway offers a reverse proxy to redirect or route requests to endpoints of the internal microservices. The gateway provides a single endpoint or URL for the client apps that internally maps the request to a group of internal microservices. This routing feature helps to decouple the client apps from the microservices, but it is also pretty convenient when modernizing a monolithic API by sitting the API in between the monolithic API and the client apps. Then you can add new APIs as new microservices while still using the legacy monolithic API until it is split into many microservices in the future. Request aggregation. As part of the gateway pattern, you can aggregate multiple client requests targeting multiple internal microservices into a single client request. This pattern is especially convenient when a client page needs information from several microservices. With this approach, a client can send a single request to the API gateway that dispatches several requests to the internal microservices and then aggregates the result and send everything back to the client app. The main benefit and goal of this design pattern is to reduce the chattiness between the client apps and the backend API. Cross-cutting concerns or gateway offloading. Depending on the features offered by each gateway product, you can offload functionality from individual microservices to the gateway, which simplifies the implementation of each microservice by consolidating cross-cutting concerns into one tier. This is especially convenient for specialized features that can be complex to implement properly in every internal microservices, such as authentication and authorization, service discovery integration, response caching, retry policies, circuit breaker, rate limiting and throttling, load balancing, logging tracing and correlation, headers, query strings, and claims transformation, IP whitelisting. Let's look at the benefits of API Gateway. It insulates the client from how the application is partitioned into microservices. API Gateway insulates the client from the problem of determining the location of service instances. It provides the optimal API for each client. It also reduces the number of request round trips. For example, the API gateway enables client to retrieve data from multiple servers with a single round trip. Fewer requests also means less overhead and improve the overall user experience. An API gateway is essential for mobile applications. It simplifies the client by moving logic for calling multiple services from client to API gateway. API gateway translates from a standard public web-friendly API protocol to whatever protocols are used internally. API gateway pattern has some drawbacks as well. Increased complexity. The API gateway is yet another moving part that must be developed, deployed, and managed. It increases response time due to additional network hop through the API gateway. However, for most applications, the cost of an extra round trip is insignificant. How to implement it? Today, the most popular available implementation to realize an API gateway solutions are Kong, it's an open source, Spring Gateway, open source from Spring Cloud, Amazon's API Gateway, Microsoft's Azure's API Management, and Red Hat's 3-Scale API Management. Thank you very much for watching this video. If you found this useful and want to know more about microservices architecture and its features, principles, difference between monolithic and microservice architecture, please go through my other videos on my YouTube channel, Cloudbase. Thanks again.